Good afternoon, ladies and gentlemen. So today we'll introduce our work on histopathology whole site image analysis with heterogeneous graph representation learning. So here are the authors and their institutions. So first, let's start with some quick summary of our work. So in this work, we propose a novel framework for whole site image analysis, which leverages a heterogeneous graph to learn their interrelationships among different types of nodes and edges. And then we propose a graph aggregation algorithm, which is here, that once we construct a heterogeneous graph from patches, we will learn the graph with our proposed heat net, basically leveraging a transformer, and also use the pillar pooling to pseudo-label pooling to get the graph level representations. And then we can obtain prediction for the classification task, whether the WSI is of cancer, which stage is it, and which type is it. And then finally, we will have a localization method based on granular causality to visualize the important patches. And then here are the contents. Then we'll go through further details. So first, for digital histopathology, we use whole site scanners to digitize glass slides containing tissue specimens into whole slice images and at really high resolution. So typical image size is at 60,000 times 60,000 of gigapixel. So on the one hand, it's very time consuming and tedious for pathologists to manually inspect the WSI due to the huge size. And another way is the image is too huge to load it into the memory, so that we need special technique to deal with this gigapixel WSIs. So machine learning solutions are introduced to reduce the workload on pathologists. And recently, traditionally there are multiple instant learning methods. But recently the emergence of graph learning also provide powerful solutions to WSI analysis, which is our focus. So let's go to some simple definitions. And then we define a heterogeneous graph having 4 components: the set of vertices and set of edges, and each vertex is mapped to a node type by a function tau, and also each edge is mapped to the edge attribute by a function phi. And then we need to define the granular causality. That is, if excluding one variable x can lead to better prediction, then we conclude that x granular causes y. We have the problem to be the whole site image classification. That will focus on classification problem like whether the WSI has cancer, which type it is, and which state it is. So that given WSI S and a heterogeneous graph G, so we aim to predict a label Y with a general model M. So basically our heat model. And then we also aim to assign an importance score to each node as the causal contribution of each patch to the localization. So here are the contributions, basically what's similar to the summaries. So here our main contribution is that we define a new data structure of using heterogeneous graph that introduce a nucleus type attribute to each node, so that we can model the meta relations in WSI. And then aggregation, we use the heat architecture and the PR pool, which will be introduced later. And then finally, we make use of granular causality for visualization or localization. So here's the overall framework. First, we use also segmentations to extract patches or whole site image. And then we use a K-net to extract the node features. Then we use COFNet to predict the node type, which type it is. Alternatively, you can use unsupervised method, for example, K-means clustering. Right, so for personnel, you use edge attributes. We use personnel to compute edge attributes. So in the end, we will have a heterogeneous graph. Then we use a heat net to aggregate the features, and then we obtain the node features after going into our heat aggregation. Then we will have used the PR pooling pool by each node type. You can see there, for each node type, we have cluster of nodes. Then for each cluster, we pull the node feature into one, a feature vector in the end for each cluster. Then we aggregate the node pool feature from each cluster to get the final representations. So which is predicting whether the whole site image having cancer or not, which type it is, and which stage it is. And then finally, we will have a causal localization method, making use of granular causality to visualize which patch is important to the prediction. So let's go into details. So first, we have instant selections. We use also thresholding method, which is commonly used to automatically segment the nucleus from input histopathology images. And then we extract patches of patch size 256 times 256. Then we output a uniform patch level image with its corresponding patch coordinates. Then we predict the node types using HoverNet classifier. By using the majority vote operation, we can find the most frequent node type, that is the node type of that patch or node. All right, so here's a visualization of the results. So in the end, we will have a heterogeneous graph. Each patch is assigned to its own node types, visualized by different colors. And on the right-hand side, we have the heterogeneous graph constructed with different types of nodes and each different edge attributes. And then for edge construction, we use Pearson notch to determine the correlation or cosine similarity of the feature vector of the nodes, between the feature vectors of the nodes. Here we highlight that our heterogeneous graph definition highlights the meta relations in the WSI. You can see several examples below specifying different meta relations between the biological entities in the WSI. And then we use H-algorithm to propagate the information. That is, for each edge, we use the linear transformations to get the key value and Q-related vectors. And then we use the edge linear transformer to get the edge to transform the edge attribute, so that we can incorporate edge attribute in the final computations of annotation scores. So that through our annotation scores, we can get the latent feature for the current layer. So after propagating through L layers, we will have target specific aggregation to get the final feature or final representation of each node. So that to pour the node representation into graph level, we'll use the pseudo label pooling. So basically each node will assign to a cluster, which is according to their node type. And then by pulling through all the nodes, node features within the cluster, we can get the node feature, a pooled feature of each cluster. So that by taking the mean or sum of these pooled features, we can get the final graph level representation. So we use cross entropy to train the model, and also we use the granular causality to visualize the nodes. So for visualize which nodes is important to the final prediction. So that for data set, we use TCGA dataset and Chameleon for visualization and compare with different MIL and the graph-based method. So here the result, we can observe that our method is constantly outperform the serial flood models. And then we can observe that for qualitative evaluation, our model can better outline the important regions. And then here are the operations on different GNN architectures and pooling methods. Thank you very much.